Can you hear me? So good morning, everyone. It's a pleasure to have Juri here today. So Juri is a particle physicist, as you know, and he works with dark matter and neutrinos. He did his PhD at the Max Planck Institute, then a sequence of postdocs, starting in Florence, then Southern Denmark, and Ohio State University, and the University of Stockholm. Now he's a professor at the University of Liverpool. And today he will be talking about dark matter detection using AI and superfluids. So please, take it away.
Thank you. My pleasure to be here. So, who has, like, professionally to do with dark matter? Can you show your, by show of hands, how many people work with dark matter? Okay, right. That's good. It's a good percentage. In general, what I can say about dark matter is that we basically know nothing about it except that it's there, right? And the evidence that we have is based on gravity, right? So you know, any gravitating system basically measures the total mass that is sourcing this dynamics of this gravitational system. So the point I want to make here is essentially that we have evidence of on vastly different scales about the existence of this phenomenon that we call dark matter, right? So we can look at the rotation of galaxies and we see how the stars move in them, and we basically see that what we expect from just counting stars and multiplying by their mass and expecting a certain force from them, we kind of understand the force balance and know that for stars not to fly away, they should be on orbits with velocities that are around here, right? Rather low. But we actually see velocities that are way higher than that in galaxies. And then, you know, just to explain the fact that the stars are not just flying away into space, we have to introduce additional mass. At least one of the hypotheses is saying there is more mass that is actually creating a stronger force. Thanks. And that stronger force keeps the stars together in the galaxy. That's one scale or one system where we know there's a phenomenon of this dark matter, or that we call dark matter. And the other system, for example, is really much bigger, right? So the galaxy is maybe of the size of a few kiloparsec, right? And then we also have systems of galaxies that are more of the size of megaparsecs. So they're thousands times larger, and we see the dark matter effect there essentially by looking at how the system bends light, right? So if you have a heavy gravitating system, it will bend light. So if you have something, some mass distribution, and you have some like star or something behind it and observe it from this direction, you see how the light is being bent, and by that you can reconstruct the mass that is bending is essentially caused. You reconstruct the lens. And then you can calculate how much mass you expect, and that mass is much larger than what you expect from just counting stars again, right? So you again see evidence of some missing mass. You could also actually try to mess with this a little bit and say, okay, maybe it's not missing mass, maybe I just don't understand the force laws correctly, right? We know Newton law describes the rotation of galaxies very well, but we can actually change it. We can say, okay, maybe in this range where this outskirts of the galaxy, it's far away from the stronger source of the stars, gravity is weaker, or like the gravitational force or acceleration scale is weaker here, and I modify gravity at lower acceleration scales, just patch it together with another theory that enhances the gravitational pull once I hit a certain threshold in terms of acceleration. Yeah, this is called modified Newtonian dynamics, MOND. Okay, let's do this exercise. And what happens is, if we do that, we can actually, from quite general grounds, just doing dimensional analysis, saying if we have a characteristic acceleration scale at which we modify our dynamics, and we want to scale the systems, right? So if we modify it in one system and want to apply it to another system that is maybe heavier, we know that the size of the system scales like the square root, or the radius of the system like the square root of the source mass, right? Doubling the mass of the system, you get a square root times the characteristics. The radius will be larger by square root of 2, right? This is the scaling law you can just derive from fixing basically a constant critical acceleration at which you modify your theory. Okay, knowing that, I can basically go ahead and plot different system masses in terms of their stellar mass, and look how the characteristic radius or the characteristic volume will change when I go from one system to another, right? So in this scaling with modified Newtonian dynamics, the scaling goes like, you cube this, it scales like mass to the 3/2, and this is the slope of the line that you get. So you can, for example, adjust this critical acceleration parameter to fit your spiral galaxy that I was showing you, of the size of maybe 100 kiloparsec across. But then you see that essentially the scaling will fail in small galaxies that are only like 1 kiloparsec. And also it will fail in clusters of galaxies that are megaparsec across, or like a few megaparsecs across. So that essentially, this simple argument really kills the whole idea of Mond, but it's just looking at this simple graph. So actually, if you do the plot, or like you do a line through that, it really shows you that the modified scale should scale, the volume should scale like the mass, right? You double the mass, the volume should be double as large. You triple it, should be 3 times as large. So that essentially scales like a cloud of particles that are just hanging out there. Or you have to do something else. You have to modify gravity in a smarter way than Mond. Maybe it's possible, but it's quite a challenge. So I haven't seen a consistent theory that really describes this dynamics. So the simpler, let's say, approach, at least the more straightforward approach that we as particle physicists kind of take, is saying, well, it's a cloud of particles. So yes, if you double the mass, it's kind of doubles the volume because it has some sort of density. So in that sense, it's like, or we expect that dark matter is some sort of new particle which we have no idea about how it interacts, but it's all around ourselves in the galaxies. Okay, that's kind of the framework that most of us believe in. Right? It's again no guarantee, but this is kind of the framework that we are kind of living under. Now this shows again a historic plot. This is essentially from the time when I started my PhD. And I think it's a bit later than you joined Heidelberg, but it was like basically when I was starting my PhD in Heidelberg. And back then people used to draw a lot of squiggles around particles and call them super symmetric. But it's a long time ago. But essentially, what this shows you is a mass of this hypothetical particle that people were like, drawing on the x-axis, and the strength of the interaction on the other y-axis. And this dashed line, those dashed lines, are the sensitivities of the xenon experiment, essentially a big tank of xenon there, where people wait for interactions of the dark matter particle to happen with the xenon atoms, and then to try to find the signals, right? And basically making it bigger increases the sensitivity, and you can probe smaller interaction areas. That's the name of the game. And what is being plotted here, this very bright color, is the so-called naturalness parameter, right? So people were basically saying in the framework of so-called supersymmetry, there is a certain naturalness argument why those particles should be of certain mass and why the interaction should be of certain strength. So this green region, people were arguing, yes, this is very natural for the particle to have those interactions. And if you go to smaller interaction areas, you will have to fine-tune your parameters, and then the theory is unnatural. It's unlikely the dark matter is there. Hence the argument, the experiments like xenon 100, having 100 kilogram of xenon, should in principle be able to detect dark matter. And xenon 1 ton for sure should see it. Okay? So what is the situation now? We're there. Yeah? We have like multi-ton experiments that are actually testing this parameter space but see nothing. So essentially, would the conclusion be that nature is totally unnatural, or maybe not? Right? So then we actually have to maybe change the way we think about naturalness. And for naturalness, in general, for naturalness arguments, I would like to show you my favorite animal, which is giraffe. I love giraffes. It's actually amazing. So if you study the giraffe, you see on this chart that has the mass of animals, different animals. Maybe there's a mouse here, there's like an elephant, and then you have their blood pressures. You can have typical blood pressures for different animals. And you can fit a graph through that, and they follow some sort of more or less flattish line that increases with mass. But the giraffe is totally off the charts, right? The giraffe is totally unnatural. So if you would like to find the giraffe, if you would theoretically like theorize about different animals and try to find the giraffe in the animal kind of kingdom and basically predict its blood pressure, it would be totally impossible to do that based on your model of this animal blood pressures, right? And the reason for the giraffe being so unnatural, essentially its long neck that developed in the evolution, and it has a certain geometry of vessels that go around the vertebra, and it's essentially topologically fixed, right? You can't unwind it in evolution. It just goes in a certain way. So in order to, if you want to have a long neck to eat, branches up the tree or whatever, you need to build a bigger heart. So it increased in evolution its heart. It actually became a very, very powerful pump, and also developed a very unique cardiovascular system that people are studying to understand stroke. It's actually a very interesting animal. So the reason why the giraffe is so unnatural is basically its production mechanism in the early universe, in the early planet. Yes. So so maybe it's not very useful to think about naturalness when we think about nature, but try to really not model the system in a very simplified way, having like spherical cows that will never describe giraffes. So it's better to try to really capture the full kind of breadth of different models and possible species. And in terms of dark matter, it means that we really have to maybe be more agnostic about the mass and interaction strength and just try to fill in the space that we want to explore. So what I like to show here is essentially a dark matter mass versus interaction area plot. And in this mass range, that is well below the mass of the proton is around the GeV, right? This is 10 to the 0 here. And well below, you have some dark matter candidates that behave more like a wave. And their sensitivity is very good, like axion and axion-like particles. We can probe the cross-section areas very well and go down, and this is being also heavily explored. On the other hand, if you have heavier dark matter, I will show you why these experiments like xenon are quite good at detecting dark matter as heavier than the proton. You also have a very good sensitivity. But on the other hand, there's a really huge gap where the sensitivity is pretty terrible, actually, compared to what we see here in terms of interaction strength. What we see just a little bit below the proton mass is really, really disappointing, right? So the goal of kind of my work and what we collaborate on in Liverpool and others is to push our sensitivity to lower dark matter masses. And it's actually a technically challenging task, because the dark matter particles are so light they deposit very little energy, but they're still not behaving like a wave where you can use this collective phenomena to actually test them. So it's a technically difficult but interesting region. Then I want to talk about two directions here. One being the superfluid helium-3 experiment that I'm collaborating with in England. And the reason why helium-3 is interesting is, one, because it has nuclears, it has spin, right? It couples to interactions that are sensitive to spin. This is like, for particle physicists, it is an interesting avenue to explore. And on the other hand, just the kinematics. If you look here, the blue graph is the typical mass, typical energy that a particle of a certain mass would deposit when it hits a xenon atom that is about 130 times heavier than a single proton. And this threshold of sensitivity for xenon is around the keV scale, so it only can probe masses very well that are above the 10 GeV, and below that it exponentially loses sensitivity and is quite blind to stuff that is lighter than a GeV. Just because it has a certain energy, minimal energy it can see, and the kinematics is such that you basically lose sensitivity once you go to those lighter masses. So the system of helium-3 is in that sense better because it's more matched in mass to light dark matter. Just if you have a billiard ball that is very heavy and is being hit by something light, it's not reacting very much. If you have a billiard balls that are comparable mass, you have an interaction, you kick it, you transfer more energy. So it's more efficient to transfer energy to like a lighter nucleus like helium-3. And you see that below the GeV scale, it basically receives more energy if it's getting hit by the same mass of dark matter particles. In addition, the Quest experiment that I'm going to present in a second has a lower threshold in terms of what kind of processes it's sensitive to. And the goal is really to be able to resolve interactions at the electron volt level, at the EV level. So about an order of magnitude, 3 orders of magnitude lower than the xenon threshold. And how this is actually being done is very interesting, because it's really a tiny quantum experiment. And on the left, you see a typical dilution fridge. It's like a multi-stage kind of apparatus that cools your system down to millikelvin temperatures. And this is actually really important because only then the helium-3 becomes a superfluid. right? And the experiment size is actually tiny. This is the size of the cell, and just for the reference, this is we used to use this for paying for things. It's called money, and this typical kind of UK kind of coin is this big, right? And so the size of the typical volume of this experiment that is actually supposed to detect dark matter is really tiny. It's 0.5 centimeters or something in size, so it's maybe 0.3 grams of superfluid helium in one cell. And we have maybe 3 or 4 cells that are operating at the same time, so the volume and mass is definitely not the ton scale experiment that we have with xenon, but I will show you that it's still doing something useful because it's pushing the threshold, and it's important to push the thresholds at the moment. It's more important to push the thresholds than having large volume, at least at the stage where we are now in the sensitivity. Okay, so having that, good. The superfluid properties of the helium-3 only emerge when the atoms are forming Cooper pairs. Why? Because the helium-3 is not a bosonic atom like helium-4. It's fermionic. But when it forms a pair, it actually becomes a boson, right? You know, boson statistics and fermion statistics. So it can bosonize by forming pairs of atoms that are bound, mutually connected basically in the system below this characteristic binding temperature of about a millikelvin. And here you have an interesting property because you don't just have the spin of the helium-3 atoms, you also have the Cooper pair that has intrinsic spin because the particles just spin around each other. And you have essentially have different ways to arrange the spins. You can essentially align the total spin of the atoms with the orbital spin of the Cooper pair, or you can anti-align it. And in the anti-aligned phase, where you basically cancel the spins, you have a more symmetric phase, that is the so-called B phase. And when they're aligned, you have a less symmetric phase, the A phase, that is less stable. If you go down at a fixed pressure, you go down to lower temperatures, you first, for example, create the A phase of the superfluid, and then you go to the B phase. So it's a very complicated, interesting system, where we're also looking at the phase transition here between A and B, and it's a first order phase transition. It's a fun system to play with, and kind of you can think about the early universe dynamics and maybe have some analogies there, but it's kind of a different work package of the experiment. So what I want to talk about now is really like the work package A, how we call it, even though it's running in superfluid phase B, where we search for dark matter. So it's really going to lower temperatures, creating the B phase, the more symmetric one, the more stable one, and then just observing it and seeing if we can detect any interaction of dark matter particles with that superfluid phase. And how this is being done is also very interesting, because when a hypothetical particle hits the helium, it can ionize it at larger impact energies, and you can create multiple photons and use it for subtracting backgrounds. This is one way of doing it, but then again, you can't really push the thresholds to very low energies, because this is happens at larger impact or larger energy transfers. When you really want to go to the lowest energy transfers and be sensitive to processes around the electron volt, you are really mostly creating so-called quasi-particles that are just the effect of breaking the Cooper pairs, right? So if you break a Cooper pair that has a binding energy of 10 to the minus 8 electron volts, it's quite easy to break. You create defects in this liquid, and those defects are called quasi-particles that we want to detect. And how this is being done is again quite fun. You are we have really impressive colleagues at Lancaster University that create those nanowires that are like very, very thin wires that are being, after fabrication, they are being submerged in the superfluid phase in this little cell that I was showing you next to the penny. And what happens now if when you put two wires in the system, they can vibrate, and they, as a typical system that vibrates, they have resonance frequency. So they have a typical self, frequency at which they amplitude is maximal when you excite them. So yeah, if you're on resonance, and this resonance frequency depends also on the friction inside the fluid, right? But the friction actually depends on this force factor, yeah, you don't really have to understand all the numbers here. The important fact is this n. And the n is the number density of particles of those defects in the fluid. So changing the number of the defects changes the force on the system, right? And that basically changes your resonance condition if you change the friction force. And that can have a strong back reaction effect, because essentially the driving force you have to apply that translates into an amplitude, how strong the thing kind of oscillates, really varies very fast when you're close to the resonance. Okay? So in principle, what you do is having two wires, where one wire is basically vibrating and heating the superfluid, and the other one is picking up the quasi-particles that you are producing, and you can essentially measure very precisely how much energy you put in this heater wire with this temperature wire. This is how we do the calibration, right? So we have a direct connection between the injected power and how the resonance width changes, and this allows us actually to create the world's best thermometer in this very cold system. And now the search for the dark matter particle essentially is switching off the heater, but then we know if you have an interaction, right? If you have an interaction in a superfluid cell, you will have some particle that scatters, creates quasi-particles, change the friction force in our wires, and this basically can tell us how this temperature will change and then drop again. So we expect the number of particles to increase. I have to tell you there's a little hole where they diffuse eventually out of, and so the temperature will go down again after a relaxation phase. So this signal can be searched for, and this is essentially something that my experimental colleagues now, after the calibration, are using to analyze the data or take the data. Still, the data runs are still taking place, and we're gonna soon come to the phase where we will be able to really analyze the data and see if there are actually any events. So I want to show you the reach, right? You can convert this expected flux from dark matter particles that come from the halo, from our galaxy, given the parameters of the experiment, like the threshold of the energy threshold, and the volume basically tells you in this parameter space where you see the dark matter mass and the interaction area, they tell you to what parameter space you're actually sensitive to. And when we analyze the data, we should be able to cover this so far unexplored red territory that other experiments are not being sensitive to. And you see this is essentially the mass range goes from 100 MeV or like a few 100 MeV down to maybe, what is it, like 30 MeV, especially if we use this particular readout technique that is called the squid readout. This is another like super cold quantum technology that is very sensitive to changes in the voltage that we are using to read out the signal from the nanowire. Yeah, these two things, those two lines are the difference between this essentially quantum device that reads out the signal from the nanowire, or a conventional, room temperature readout device that has a somewhat larger energy threshold. Yeah, so essentially you see already in this plot that sensitivity and lowering the energy threshold buys you a lot of new parameter space that you can explore in these experiments. Even with a tiny, tiny cell that is a few cubic centimeters in size, you really cover new territory, and in that sense you're really competitive with experiments that are maybe multi-ton scale but explore a different parameter space, right? So we're going in a new direction. On the other hand, it's a prototype experiment. If the technology can be established, you could think about bringing it underground. Yeah, we are now running on the surface. If you bring it underground, you have a suppression of the backgrounds from cosmic muons and other backgrounds that you want to get rid of. So that will also improve the sensitivity, and then you can go to smaller cross sections when you suppress the backgrounds, right? So in general, in these plots, when you have less background events or more volume that you observe, you can probe events that happen more rarely. In that sense, you go to less interaction area, so you go down. If you are sensitive to lower energy deposits, you go to lighter masses, because lighter mass dark matter deposits less energy. You go in this direction. So pushing in general in this direction of the parameter space is the goal for those interactions. By the way, I would like you to interrupt me. It's not formal, so I think if you have any questions, please ask me at any time. I'm happy to stop. Yes. Oh, it's the binding energy of the Cooper pair that is 10 to minus 8 eV or something. It's not control. I mean, it's a fixed number. We just know it's 10 to minus 8 eV or something. It's the energy gap where uh, when this effective interaction between the helium atoms is strong enough to bind them in the Cooper pair. And if you deposit energy that's above that, you break it. So in the end of the day, actually, it's a good question. In the end of the day, this is something that ultimately limits the sensitivity. This delta being 10 to the minus 8 EV, right? If you have a process that is less than that, it will not break your Cooper pair, so you will not see it, right? No, go ahead. Mm-hmm. Well, now we are sensitive to maybe even with a squid rate out 0.1 EV, right? So we are actually seeing 10 million Cooper pairs broken is something that we actually can detect, right? This is our sensitivity. If we improve that, there's still 7 orders of magnitude to go before we hit the physical limitation of the system. So it's much more, it's still at the moment much more technologically limited than it's physically limited by the system itself. So in general, when you think about like the sub-GeV dark matter field, people typically find systems that have some sort of an energy gap, like a superconductor, right? Or something that has a small energy gap. When you hit it with something light and deposit a little bit of energy, something happens, right? It's not enough just to be able to to have an interaction. You also have to see it. So you have to actually have a signal. So for us, the signal is breaking the Cooper pairs, creating this change in the friction and so on. If there is a way to improve the readout, you really kind of linearly improve the sensitivity in that plot. Every kind of, order of magnitude that you gain in lowering the threshold essentially linearly scales in terms of mass that you are able to probe here. So yeah, it's a very good question. Other questions? I think it's yes. Yeah, eventually you will have also like noise limit of the wires. Yes, good question as well. Yes. Other questions to that whole kind of superfluid topic? The different backgrounds. There's a technical limitation from the noise from the basically wire. There's mechanical vibrations. So we have actually now a background that we're not sure where it's coming from, but we think it's kind of general kind of vibration of the whole apparatus. There's also cosmic backgrounds but this is well understood. You just can veto the cosmics. Getting rid of mechanical vibrations is much harder than getting rid of the cosmics at the moment. So we will have to think more about this, how to isolate. There are techniques. In principle, there are like special tables for laser experiments, right? Where the people put the laser experiment on this separate kind of thing in the building, and it's like noise, like vibrational noise reduction. But this is difficult. Yeah, good. Other questions? Yeah. Oh, the overall, I mean, again, it's the experiment had a budget that was about 1 million. So it's, yeah, £1,000,000. Yeah, it's like 1.2 million euros or something. Yeah. So it's rather low, and it's mostly paying a couple of postdocs because the dilution fridges were already in place, and people. So in principle, it's kind of a collaboration between low temperature physicists and particle physicists, and the main thing of the experiment was actually bring the people together because a lot of parts of the experiment were already there. Lancaster people were experimenting with the nanowires, and low temperature people play with superfluid helium just for fun, and they're doing their experiments. They're having fun. We are having fun. So it's about like bringing people together and try to say, hey, there is something in particle physics that you actually can do with the system. So I think this is also something always nice to look out for. Who is doing something that you might actually use for fundamental physics? I think that's also a very interesting kind of link in this regard. So yeah, thanks very much. It's a good question because many things, sometimes you don't have to build everything from scratch. Yeah, great. Okay, right. So now we're more or less at halftime, and I just want to briefly mention one idea that I think it's nice for bringing the threshold even lower is saying, okay, what can we do if we don't care about individual interactions, but rather say we have a very good thermometer, and we just don't care about resolving the interaction. We just want to integrate over time and see how much temperature change are we sensitive to. So you basically plot the temperature that you measure as a function of time. So you have a temperature, you have your time, and my colleagues are actually taking data, and it looks more or less like that. So you see temperature measurements that stay around the millikelvin temperature, where you have the superfluid phenomenon, and that at some point it kind of diverges when you have too much kind of external heat injection, and the system stops being superfluid. So that happens maybe after a week, and you typically can run the system for a week, and we have those precise temperature data. So now we're trying to convert this essentially in a sensitivity to total energy injection that can be deposited without resolving the individual particle interactions. So this is just for elastic scattering, but we're thinking maybe about other processes as well, like maybe the axioelectric effect or whatever particles you can use to deposit energy to. I think that should be quite interesting, the reach for new physics, in the sense of, okay, what can we deposit any power in our detectors? And one thing what I found also quite fun, this is a little bit speculative, but I think it's an interesting direction to explore. What if dark matter has a long-range mediator? And long-range means that it's, has such a size that it will probe multiple atoms around it, maybe about a cubic centimeter or something. When that happens, right, if the interaction is of that length or longer, you create actually macroscopic potential that brings or binds the dark matter particles when they're inside the Earth very tightly, well, at least slightly stronger than gravity, and you can have a very, very strong enhancement of dark matter abundance around essentially in the crust, without really being able to see it, because dark matter is moving very slowly there, right? It kind of stops, thermalizes, and moves at typical thermal velocities in the Earth, which is much slower than the halo. So in that sense, it's even harder to detect than the halo particles, because they carry even less energy. So on the other hand, if you have this kind of huge enhancements, like many orders of magnitude in terms of number density, with the total power injection without an explicit energy threshold, we are still able to rule out, I think, a large fraction of this parameter space, but it's something we're currently exploring. But I think it's an interesting idea, saying just, okay, what happens with locally bound dark matter that might be actually quite strongly enhanced in terms of the local number density. Okay, so just another side note here. Do you have an idea, if you don't have the long-range mediator, why I wouldn't have such a strong enhancement in all of the parameter space? It's more like a specific question for the dark matter community. In terms of could I have earthbound dark matter? That's the other question. Typically, yes, very good answer. Yes, I see. Typically, yes, of course you have earthbound dark matter. But if you go below the masses of 10 GeV, or even around the GeV scale, typically what happens is you bump into normal atoms inside the Earth that have also terminal velocities, and those velocities are large enough to just kick you out from the gravitational potential of the Earth. Right? It's essentially like we're having something like helium or hydrogen in the atmosphere. It will also evaporate and just fly into space. Yeah, so in principle, if dark matter is as light as a GeV and below, it will evaporate from the Earth unless you have an additional potential. It doesn't have to be strong. It has to be comparable to gravity, maybe factor a few stronger than gravity. So you can have a very small coupling, but the range could be of order of centimeters, and it already will keep you bound in the system. Yeah? Okay. So now, moving on to a slightly different topic. Well, same topic, searching for light dark matter, but slightly different approach. I said, again, with kind of my strategy is to try to find new ways of searching for light dark matter, and the name of the game there is, again, how can we achieve lower thresholds, finding systems that have lower energy thresholds. And an interesting avenue that we kind of started exploring with a couple of collaborators are organic molecules. And I want to show why those are interesting. So in general, when we have a dark matter interaction, this is the rate per energy in the detector. You can divide your kind of theoretical calculation of how you predict this interaction rate into several parts. There's one part that depends on the astrophysics, on the velocity of dark matter, how it kind of comes in from the halo, and this is fixed. This is just given by nature. There's also a form factor, let's say, how that tells you, based on the model of dark matter that you have, whether it has a long-range mediator or short-range mediator, tells you how efficiently it transfers energy to your system. It is also given by nature, and we can't really affect it. We just don't know it, so we kind of plug in different models. But what we can affect is actually the system that we are testing the dark matter with, that has some sort of ground state and an excited state. And there is a probability for the system to go from the ground state to the excited state. And here we can play with it. We can modify the system, we can choose different systems, and I want to basically discuss what systems are actually beneficial to optimize my search by being sensitive to low energy deposits, and where the probability of this transition is actually large. Right? So in principle, we have a dark matter particle again, hitting a ground state, exciting it, ideally emitting a photon that you have, you could detect it. And how could we maximize this probability when we do the calculation and expand this operator that we're seeing here? In the leading term, we see that it's really well approximated by the so-called dipole moment of the system. Right? So in principle, if we have this molecule, so if we think about the molecule that is being excited, the thing to look for is some molecule that has a low transition energy, as I said before, maybe in the range of electron volts, and a large dipole moment. I mean, you can do a precise calculation where you have the full kind of electron orbital predictions, and you can do a density functional calculation to predict the transition probability. But as a rule of thumb, it will happen when you have a large dipole moment in the molecule. So we try to optimize for that. So thinking about organic molecules, there's a lot of freedom to play with, and I will show you why that is the case. So going back to high school chemistry, if you remember the carbon atom, it's a very cool atom. And why is it so interesting? Is because you have 4 electrons that can actually do valence bonding with neighboring atoms, and it has different states of so-called hybridized orbitals. Right? It has 2 orbitals in the s ground state. Here you have 2 electrons in the free carbon that live in the state with angular momentum. But when it interacts with neighboring atoms, they are getting hybridized. They go on the same energy level. So this is called the sp3 hybridization, because they're distributed across the 0 angular momentum and the 1 angular momentum states equally, making them completely kind of uniform in a sense that they're kind of democratically distributing the electrons across all the neighboring atoms. So the C basically creates 4 bonds that are essentially forming this tetrahedron with about 104 degrees across all the angles. It's just like a nice, very symmetric tetrahedral molecule. Here in the case, it's hydrogen atoms that are bound to it, but it can also interact with other carbon atoms. This is kind of the simplest hybridization of the carbon atom. But you can also hybridize in a different way, where you hybridize only 3 electrons, s with 2 p orbital electrons, and 1 p orbital electron is kind of separate, so it's kind of special. And that happens, so you actually create a system where C atoms, for example, share 1 bond here. This is called this binding orbital, the sigma orbital. This is more tightly bound. But the other one, the unpaired guy, which has still angular momentum, this Z orbital, goes out above and below, and it has the so-called pi orbital bonding, which makes the bond stiff, so it can't rotate. Really, it kind of fixes them in one plane. And the other ones go out here, and you have a 120-degree angle in between those atoms. In this case, it could be hydrogen, or it could have other carbon atoms that are connecting to it. It doesn't matter. You can have links to other atoms. But the interesting thing is, these pi orbitals have typically lower binding energy, so you can excite them more easily. So there's already the first hint what kind of systems we're interested in, namely systems that have double bonds, or this kind of hybridized orbitals. And that makes our kind of system very diverse, because here, okay, let me just show you this annotation for organic chemistry, is that carbon atoms just have a dot, and if you have a double bond, you have like 2 lines, If you have a single bond, you have a simple line. So you can have complex molecules that you express just in terms of simple, like single and double lines. So this, for example, will be 3 carbons. So if you wanted to draw this properly, you would have 3 carbons that are surrounded by hydrogen atoms in all directions. But you just drop the hydrogens and just draw the carbon connections as kind of lines. If you wanted to create a double bond between, so this is actually a 4 carbon thing. So if you wanted to create a double bond here, you just draw a double bond like this. So that's kind of the organic chemistry notation. And there are very interesting structures that are based on rings. Yeah, you know, we like symmetry, and this hexagon ring is called benzene. And here you have essentially 6 carbons sitting like this, and they have alternating double bonds. So you have here sigma orbitals, but you have also the pi orbitals sitting around every atom, right? Because they're kind of symmetrically delocalized across all the ring. And those pi orbitals basically create this nice electron cloud that can be quite easily excited. So this is a very fundamental structure that already goes in the right direction of having a very nice property. Trouble with benzene itself, it's very symmetric, so the ground state or the lowest lying transitions are forbidden by certain symmetry properties. But the direction of model building, let's say optimal molecules, already tells you, okay, we can actually play with this kind of Lego balls. You know Lego, the kind of children's toy where you can combine different connections. Yeah. So this is kind of our building blocks that we can actually play with to build the target that we actually want. Now, just as a proof of principle, my friend Carlos and Ben and what is that? Javier Colar have actually set up a really simple but very amazing proof of principle experiment that was basically had a very much lower budget than $1 million. So basically took a paint, a can of glorified paint sealer, just like some organic molecule that they had sitting there in their basement, just a can of this organic stuff, put it into a lead kind of detector in their basement. So they basically put the can in the middle, put the lead around it to like reduce the amount of cosmics that come through, have actually a little plastic scintillator VTOL to actually read out some of the cosmic events to reduce the background of cosmics, and put 1 photomultiplier. You know what a photomultiplier is? It's essentially a thing that is very sensitive to detecting photons. And they were waiting for this thing to emit a flash of light when it was hit by a dark matter particle. So just having that for 3 months in their basement allowed them to basically be completely competitive with much larger kind of silicon-based detectors that are state-of-the-art, right? This, I don't know, a few K dollars worth experiment immediately got on the kind of frontier of the technology that we currently have for this sub-GeV dark matter detection that couples to electrons. Very interesting. So based on that, we said, okay, if this paint sealer experiment can basically do such a good job in testing this parameter space, couldn't we actually improve on this by choosing a better target? Apologize. Well, if you have a problem, or if you have a tool, everything looks like a nail, and we want to play with machine learning, because why not? And let me talk a little bit about like information and how actually self-learning systems learn. The ideal way of teaching a machine to do something for you is presenting it with information that is well kind of prepared and ideally unbiased. So this here, the royals, you can arrange them in this way, and you can give them numbers. The king gets the 1, the queen gets the 2, and so on. But this information here is biased. Why? Because you say, like, for some reason the king is more important than the princess, right? So this automatically you put. Thank you. That's very nice, actually. That's really thoughtful. Thank you very much. So in this way of presenting information, you're clearly biasing your system in a certain way. How can we avoid that? It's just by doing a slightly different arrangement of numbers, by saying, okay, we create a vector space that is not one-dimensional, but four-dimensional. And each person gets a certain number, or like a direction in the vector space. The king goes in one direction, queen goes in the other, prince, princess. So this is a basic encoding. This is called the one-hot encoding, where you create basically an alphabet of certain concepts and align them with so far uncorrelated directions. Now, if you present your system with more data that has maybe stories about kings, queens, princesses, you just give fairy tales to your system and train it. What it typically will do is actually rearrange the information that you have, and it might create a vector space that looks like this. For now, we can't really make sense of it, but if you plot it in a graph, you can actually see axis, and now it has arranged it in a two-dimensional plane, but they have created automatically an axis of gender, because the prince and king are basically on this coordinate, but the princess and the queen live in there. And it has age, basically another axis, that the princess and prince are young and the king and queen are more elderly. So basically, by running a lot of fairy tales through your system, has arranged the data in such a way that the machine has actually figured out the concept of age and gender just by processing, or by having information being pushed through it. This is what the typical network will do. Now, how about generating new data, like new concepts and new structures? Is by essentially combining networks. And here I want to say we have some data, numbers, pictures, words. And we have an encoding network, basically layers of neurons where we encode our data, maybe in the one-hot encoding with zeros and ones, give them to the network and push it through and create an internal space. Essentially, the output will be just some sort of high-dimensional vector here that we are quite agnostic about. We just know the dimensionality. So we just fix the dimensionality, for example, to be 64 or 50. You know, choose the size of the of this internal vector space just to be representative for the data, right? It has to be like large enough to capture the information. But now we create, when we encode some vector, and then we have another network that takes that vector and creates the information back. Now what we do is then running it many, many times and training it with a loss function that it wants to recreate. So the decoder learns to get the image back from the information that it got from the encoder when it put a vector in this internal vector space. There's an additional trick where you do some smearing, where you basically enforce this internal space to have a Gaussian distribution function in each point. But that's maybe a little bit technical. I will not really dive into that. But there's a certain sampling procedure that you're using to generate distributions in this internal space. But what I want to show here in a simplified way is to say, if you have this latent space, that is the internal space, and you have structures that the system has learned, like a circle, a square, and different square triangle. When the encoder basically puts in a circle, the decoder will recreate a circle. Puts in a triangle, it will recreate a triangle. But now, if the system hasn't seen anything else than those shapes, and you just give it a point from the latent space to the decoder here, it will automatically create some hybrid between the square and the circle. So it will do something like that, maybe something like a squarish shape that is kind of a hybrid thing. There's a video that I can't play right now, but if you go around this latent space, you have some hybrid shape that the system automatically generates without ever having seen anything that is not a triangle or not a square. So there is a generative aspect of this, which is actually the powerful property of those generative models. I mean, this is called the variation autoencoder, and it's known also for this image processing, where you have like a lot of faces, for example, that you give to it, and then it trains and learns how the faces look, and it creates directions in this internal space. And there is, for example, a vector, a direction that is a smile direction. So you could take after the system has trained on many faces, you can take a picture of your friend, put it there, and then if you go in the smile more direction, it will look like this. If you go into the grumpy direction, it will look like that. So it's the same vector, but you go in different directions, and it puts the smile or reduces the smile, and in the edges it always looks creepy. But it's very interesting because the system had never seen this person. You basically put an encode this person, it will be assigned a point in the latent space, and now you know that if you go left or right in the smile direction, you will have the same person smiling or not smiling, which is fun. So, what about chemistry? The chemistry also has a language, where you can formulate chemistry as a language. You can take this molecule and encode it basically in a string with the carbons and a certain rule how to connect them. And recently there's an additional development where there's a self-reference strings that are called selfies, actually, the self-referenced encoding system for chemistry. It essentially has more internal grammar, and I will tell you why this is important in a second. But the point is that you can actually write down a sentence type structure and encode your molecules in this way. Now, anybody knows this molecule? No, okay. You see, you're well-behaved people. This is ecstasy. You should know this is bad. No, okay. Okay. Anyway, the thing is with this encoding is if you have mutations, so-called like changed letters, in this older notation, which doesn't have the additional kind of semantic rules. If you change mutations, you get quickly invalid molecules, just chemically not valid molecules. But having this other encoding of selfies with the internal grammar, if you change like one symbol, you will necessarily end up with something that's still chemically valid, because it has some internal kind of balances or check structure that gives you valid molecules. And this is very good for generating new stuff, because you interchange things and you get new molecules. In terms of latent space, it shows that if you use the selfies, you get a better quality of your internal latent space. Green means like reconstructible molecules, so improves this quality. So we're using this language to actually train our models. So now, for example, when we take this so-called QM9 data set and learn it, it's QM9 means they have like up to 9 non-hydrogen atoms, and this data set has 130,000 molecules that basically are mathematically complete. So all the combinations that are possible are in this data set. So if you do that and just give it to the autoencoder, the structures, and encodes and decodes them, this is the latent space here. Sorry. Okay, this doesn't work, but so this is the latent space, and we kind of can put the excitation energy as a color on this latent space. So without even knowing the concept of energy, the system automatically has basically put some molecules with lower energies in one corner of this latent space, or in one range, and in the other region essentially has higher excitation energies. So the system automatically arranged them by their property without even knowing about the property itself, which is very interesting. So now we can take another network that is reconstructing the property just from looking at this at this graph and knowing some training data. It can reconstruct basically from a training set. It can reconstruct the property on the validation set with a quite good statistical power. So this is actually very promising. So once we have done this training validation, typical validation set of the mathematically complete smaller molecules, we went to a larger data set that is called the PubChem 3 million, that has much like way more molecules, and it's not mathematically complete. So it has a more complex structure in the latent space, but you also see that it arranges the transition energies from the ground to the first excited state in this map, where the darkest color corresponds around EV energy, which is actually our target region. Now our task essentially is an interesting architecture by saying we have a generative task where we have this encoder-decoder thing with the latent space that I showed you, and we want a regression task where we basically want to have a thing that is being encoded or decoded from the latent space, and we want to know what kind of energies and dipole moments we can expect from it. So we can first of all look at the latent space position. This is something we can give to another network, so-called multi-layer perceptron. This is just a regression task, typical network for a regression task. But we also use the so-called fingerprints, kind of thing that tells you what is the three-dimensional information of of the electrons of that molecule that we can create based on the input string, and there are like algorithms to do that. So we use this information, like a more information-rich strategy to give to this multi-layer network, and it can actually predict the properties even in this larger data set very well, especially when it comes to the binding energies. It's harder to learn the dipole moments, but that's how it is. So now what we can do is essentially go ahead and look around the areas where we have good candidate molecules with low excitation energies, and then sample around them, because we hope that we find even better molecules in their vicinity. Doing that, we get a lot of molecules, actually more, like a huge amount of molecules, more than you can humanly process. So we have to do something with them to actually try to find out what is the kind of underlying pattern among them. So we're using a clustering algorithm to find the most common clusters and motifs in those predicted structures and order them, for example, by the likelihood, or like by their relative abundance. Of course, selecting molecules that have lower excitation energies and large transition moments. This is already a pre-requirement of having to for making it on this list. So now we see there are some structures that I told you about that are abundant. It's not surprising that we actually have the benzene rings, very, very common in the structures. And then we can do even more. We can try to look what motifs are most abundant if you really do a ranking according to the predicted energy and transition moments. So we already see some structures. For example, this one I can already tell you is a very interesting one, where we have connected benzene rings by these conjugated bridges. So now going further, we can see some patterns. So we see, yes, very common are benzene rings, as I showed you before, from an organic chemistry point of view, absolutely unsurprising. But conjugated rings are also good. Symmetric systems with a slightly broken symmetry are even better, because you kind of break the symmetry, allow certain transitions that were forbidden by symmetry before, and that's already a gain. And this one is also very good, because it has a low excitation energy, but again, the lowest one is forbidden by symmetry. So if you start kind of varying it, adding some additional groups and breaking the symmetry, this is actually something very good. And we see that those are promising targets. And so Carlos had actually already calculated the basically excitation energies numerically with density functional theory for this molecule without the symmetry breaking before, and it's already a very interesting candidate that luckily forms crystals, right? If you want to build a detector, it's better to form some crystal that we can put there, and ideally it's transparent, we can read out the photons. So this is already quite a good candidate. But what we did on top of that is taking our list and comparing it to the database of crystals that we know, where we know that the molecules can form crystals. And we actually figure out that those are actually very interesting candidates that are crystallizable, and our kind of colleagues at MIT in Dana Friedman's group already have synthesized them. And they had a nice way of growing the crystals, so they actually just shipped them last week to my colleague's place, where we actually will do polarized light measurements on them to not just validate the transition probabilities that we actually try to optimize for to have the low excitation energy and light transition probability, but also we want to try to use the polarized light to find whether they have some sort of anisotropies. And the anisotropy is also very important, basically saying if you have a crystal here, that if you have a dark matter or a photon or whatever interaction you have that comes in from this side, that your probability of interaction is higher than if you have a particle that comes from the other side. If you have that, you can expect modulation of signals. And this is very cool for dark matter, because we know that we are flying on our kind of spaceship, which is our Earth, through the halo with a certain velocity. So we have a dark matter wind that comes during the summer, for example, with more basically velocity than during the winter. And also when you rotate during the day, you have a different direction of your detector, so you also expect a modulation signal if your target is sensitive to directional signals. So what we plan to do is essentially improving our networks, creating a shortlist, and creating an efficient pipeline of calculating and validating this also with numerical methods like the density functional theory. And the collaborators here at Penn State and MIT can do this very efficient measurements for the polarized light fluorescence, and there's another cathodoluminescence method where you can also efficiently measure the interactions that are a good predictor for this dark matter properties. So the ideal kind of experiment that we want to build is create the optimal targets and combine them in such a way, especially having particular anisotropies, where you can create a very dedicated experiment that will have a maximum sensitivity to directional signals, especially if you have a molecule that you know has a certain anisotropy axis in one crystal, and then you have maybe 5 different crystals where we exactly know how their modulation is expected to be. You can beat the backgrounds very well by essentially waiting or basically cutting everything out that is kind of static in time and really wait for a particular modulation of your signal. And this hopefully will allow us to beat the backgrounds, because currently the big issue is that the the CCD based or the silicon based detectors have very large backgrounds, and this basically prevents them from going further in this direction. And to make this target here, that is basically background free exposure of 1 kilogram year detector, that's kind of the goal. We would need to really create maybe a kilogram scale detector that has enough like anisotropy to really be able to cut on the backgrounds. All right, that was it. Thank you very much. Questions?
Yeah, thank you, Juri.
Yeah.
Let's open for questions.
Of course.
So, regard these new chemistry composed, I think like it's elements, molecules, by the way. So you're gonna see the direction of the interaction with the dark matter because of what exactly? What's the property of the molecule that
Yeah, thank you. It's a good point. We don't necessarily see the direction. We know that the probability, let's say the F, this is bad color, the F from I to J, the transition probability coming from this direction is different than the probability F tilde from I to J here. So you can, you can basically make a plot. You know how the flux is from your dark matter based on the daytime, right? When you spin on the Earth. And then you have a rate that you expect based on this kind of functional dependence of F on direction. And then you can basically plot the rate that you expect as a function of time, and you will see something like that.
So in this case, this F tilde, for example, and F, it would be different because of astrophysical conditions, or?
No, the F are different because of the orientation of the crystal. I mean, or the property of the crystal, because the molecules typically are arranged in a certain plane. So hitting it from here maximizes the probability of the transition of the electron cloud to the excited state, and hitting it from there. And the flux that comes from the halo, that is given. We can't influence it, but we can choose a target that is maximally kind of anisotropic in terms of having F and F tilde being maximally different.
That's exactly what I wanted to know. But then in this case, I have another question. Like some chemistry molecules, they have like properties of chirality, right?
Of what, sorry? Chirality, yeah.
So have you ever talked to these chemistry friends about this kind of thing, that if it could be used, for example, to understand the other kind of interactions of dark matter or neutral particles with these molecules, for example?
Well, chirality is a property of your geometry where you have.
Give an example, maybe.
Mhm.
So if I have a molecule that has a chirality in such a direction, let's say, then if it interacts with a neutral particle, let's say dark matter in this case, it would change, for example.
Oh.
You could measure this.
Yes. Okay, good point. Okay, so you're saying if you have like a sample that has 99% of left-handed stuff and like 1% of right-handed stuff, and then you want to have interactions that would convert it, and after a while basically say, okay, how much have you converted it? So it's a bit difficult with chirality because it's very, very hard, because the number of scatterings you would need to convert even 1% of a gram in terms of chirality is still 10 to the 23, right? It's huge. So to get something that is sensitive, you would have to have something that is pure on the level of 10 to the minus 20 to 23, 24. Right? This is very difficult. But there are still other molecules that we have discussed that change their conformation, where you have a sample that is completely kind of one type, but then by bond breaking you actually can change the conformation, and eventually eventually you could build up basically part of the molecule that you wouldn't expect to have, and you can measure it dynamically by sending certain like light photons through it at a certain frequency. So potentially you could build something that is like a really chemically changes its properties by being hit by dark matter. But the thing is, with chirality, it's hard to get those kind of precisions in terms of purity. But there are other molecules that you can basically get to a very high purity to have a certain type of bond structures, and they break the bonds and change the structures as well. So there's again this kind of chemical kind of Lego blocks allow you a lot to play with many concepts. But it's a good question. Thanks. Yes. Which one? Yeah, it's running. It's running.
Can you, for example, measure cosmic particles?
Yeah. Mm-hmm.
You can distinguish it from there is an effect.
Well, they typically, yeah. So what it's being done is they put a veto. It's usually like this silicon slabs that you put on top of your experiment. So you have your experiment here. You have a silicon detector, and they basically look for the muons, and then if the muon comes through, you basically switch off, take out the data. So you veto it, and in a sense, you can't really distinguish because the signal is very simple. It's just the energy injection. So you have to really veto the muons out. You can't really distinguish it like xenon can.
A single event, you'll probably just measure the excess.
Exactly. You measure a rate, and eventually, yeah.
But what's the idea? I mean, so why people use xenon, for example, and not originally other types of molecules, other types of materials like organic molecules, which you say are exponentially.
Well, xenon, like with its large mass, it's really optimal to look for something that is in the range of 50, 60, 70 GeV and above. It's really optimal for that because it has, if you look at the cross section, it scales like a to the 4 in this mass regime, where a is the atomic number, and atomic number is 130 or something. You have like an enhancement with 8 orders of magnitude, based on your kind of base cross section, just because you use xenon versus helium, for example, for those heavy dark matter particles. And if it's heavy, again, the kinematics is very well matched in that sense that your theoretical prejudice really directed the people to build a helium experiment, which was fine, and they really covered a lot of parameter space there. But again, when you look at the cross section versus mass plane, the helium, the xenon-based experiment went all the way there because people were expecting to find something here, supersymmetry. Yeah, that was like the typical neutralino would live there. Electropic multiplets was also very well at saying some sort of like triplets, quadruplets, quintuplets of SU2. This will be also like very well testable with xenon because the thermal masses are in the tens of TeV or like a TeV scale. Xenon is it's very well suited to do that. The thing is, it's not, people didn't expect dark matter to be lighter than GeV. There's like more or less more like recent trend to say, okay, well, if you don't see anything here, maybe we actually also look there. But again, that's why you need other targets, other materials, other kind of detection thresholds, lowering the detection thresholds. It's nothing bad intrinsically about starting somewhere. Just people based on their theoretical assumptions started looking here. Yeah. Right. Yes. Whoever wants to go first. Okay. So here there was a drawing. So we have the heater wire is off. So we still have the other wire, the receiver wire in the liquid, and it's constantly being run. It's also vibrating by sending a certain voltage through it at a certain frequency that's very close to the resonance. Now, and basically we know the amplitude again from measuring kind of the voltage output. We know how the amplitude of this guy is. So now when the particle chi, the hypothetical dark matter particle, scatters in this experiment, and now the number density of those quasi-particles increases, the friction changes, So given the fixed voltage, you change the amplitude, so the output voltage changes. So you can actually say, oh, this resonant width has shifted for a certain amount of time, and after the additional particles that have been created diffused out of the box, you're back to the original width again. So if you do like a, I don't know, width h, plot again versus time, it will kind of increase and then decrease again. So you will have this bump in your width from this from this resonance that will be your signal. Oh, it's just for the calibration. Yeah, the heater wire just to really connect the energy that you inject to your output voltage here. Yeah, that's a good question. It's just a calibration measurement. Then you switch it off and then you wait for the signal. Right. That's okay. Thank you. Mm-hmm. Oh yeah, to have like more modulation signatures. Yeah, it's a good question. I mean, but what do so I'm just thinking, what do I gain from having them at the same time in different places, whether I could just like just wait and for my experiment just to rotate and take the data over time? I'm not sure. I mean, you could do, yeah. Well, okay. Now, maybe it still reduces. It's still okay. So it might still reduce the backgrounds because otherwise I will still have to assume that my backgrounds are flat in time. But this might be not true, right? Nature is not flat in time. Nature has modulations. Nature is, we are spinning around the Earth. I mean, around the sun. The Earth is spinning. So there are things that actually also modulate on the same frequency, as Dama knows. So so yes, having several experiments is definitely advantageous, and having cheap experiments also is a quite of an advantage, because you can just build it. You can build two. You can put like two experiments in one in China, like in one in Gran Sasso, and use all the mines that we have. Yeah, that's a good point. That's true. Yeah, but yeah, first we have to build a prototype and see how. Yeah, but it's a long-term project. But yes, but again, like testing the crystals, I hope it will. I have no idea what the time scale is for deployment, but I mean, we are testing the first crystals now, so maybe like next year we can say something more about it. Cool. Sorry, yeah. No, it's the same backgrounds. The same backgrounds. It's heat, it's vibration, it's cosmics, but we don't expect them to be modulated in the same way as dark matter. So we want I'm not saying that molecules have a different background than this skip SCDs, but the skip SCD is completely isotropic. It's completely isotropic, so the signal for dark matter is not time varying, while in the system that kind of we're proposing, you have a time variation, and that will allow to reduce the background, even though it's the same background for the both systems. Yeah. No, it's a good point. If you maybe build something that has some, yeah. So if you manage to have an anisotropy here, right? You will not. Yeah, the annual, yes. Mm-hmm. Yeah. No, you're right. So you can have with silicon, you can use annual modulation, to do that. I think daily modulation will be harder to detect. Daily is probably impossible. Yeah? But for an annual one, yes. You have in the summer, you have more events than in the winter, and then yes. So if you have the so yeah, you probably can, and I'm sure the collaborations will do that once they have longer data sets, multi-year data sets. They will be able to do this analysis, I'm sure. Yeah. Just of course to have something that within a year you will have to rely on daily modulations. Yeah. Good.
More questions? Well, if not, let's thank Juri again.
Thank you.